Okay, so here I go again for the umpteenth time trying to record this crap for you guys. This is like the fifth time I've tried to record this. I hope it works this time. Let's see. Oh, I hate this phone. Hang on, I gotta set a timer for my lecture here. All right. If I don't set a timer, then the videos are too long. And if the videos are too long, it takes too long for me to upload them and for you to download them. So, oh, all right, here we go again for the fourth time or however many times I've done this. Okay, measure, measuring perception. Okay. Um, a very important concept in measuring perception is the detection of threshold. In other words, figuring out at what point a critter or a person can detect something and when they can't detect it. Okay, so trying to figure out the limits of the detection capabilities of whatever sense you're talking about, whether it's sight or sound or hearing. One of the types of thresholds that's determined is called an absolute threshold, and basically that's just measuring the smallest amount of energy that's needed to detect something. So the smallest sound, the dimmest light, the lightest touch, whatever is the minimum that's required so that you can say, yeah, I see that or I hear that. Okay. One of the ways it's done is the method of limits, and that's described. There's a picture of that in your book, Figure 115 on page 13. The method of limits. So basically, what you do is you go up in different intensities in order. So you start with the softest and you go a little louder, little louder, little louder, little louder until the person says, "Yeah, I hear it." Okay, and you say, "All right." You mark the spot where they heard it, and you go loud. Then you start loud, then you go softer, 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 softer until they say, "I don't hear it anymore." Then you mark where they didn't hear it, and you keep repeating that. You go back and forth, and then you average out the points at which they said they could either hear it or not hear it anymore. So, whoops, let's see. So, for example, with vision, right? You can do this with vision, right? Here we're trying to see what's the close the narrowest distance between the black bars that a person can detect. So we start with the stimulus on the left, where the bars are very obviously apart. Then we get them closer together, like the stimulus in the middle, and then until we get to the point where they say, "Well, I can't really tell there's bars anymore. It just looks like a big gray area." And at that point, we mark, okay, that's where they said they couldn't see the bars anymore. And then we would start and going back up. We'd make the bars wider and wider until you say, oh, yeah, I can see the bars again. Okay? That's how you do that for the detection of patterns in a horizontal or vertical or diagonal position. This is an example of method of limits being used for sound, right? So as you can see, the trials are organized according to columns. So the columns are here. Uh, First trial, second trial, third trial, all the way. We did this 8 times, right? And so the first time we did it, we started at a higher intensity, and they said Y means yes, they could hear it. Yep, they can 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 hear it. Nope, they couldn't hear it no more. So we mark that. And then we start with a really low intensity. So no, I don't hear it. 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 Yes, I do. We mark that, and we do it again and again and again and again. And each time we mark the point at which the crossover occurred, where they could go from hearing it to not hearing it, or from not hearing it to hearing it. And we take all those whatever values there. So for example, this would be 99.5. This is 98.5 right here. We average all those over, and we come up with a mean threshold. We would say that in this person, the average threshold for hearing, if this is intensity of sound, is 98.5, whatever it is we're measuring sound in. Another a similar method is called the method of adjustment, and this is basically where instead of you sitting there and listening to the tones going up and down, or to the lights getting brighter and brighter, or the lines getting closer, the person that's doing the evaluating is actually turning a knob or adjusting the intensity, and they slowly move the knob or the dial until they see a change in until they're able to see the stimulus or hear the stimulus, and then not see it or hear it anymore. So they go up and then you say, "Oh, I hear it now." And then you mark where they heard it, and then they turn the dial back down. And they say, "Oh, I don't hear it anymore." And so it's similar to the first method, the method of limits, but instead of sitting there, they're turning a dial, and the dependent variable that you're measuring is just at what point, how far they move the dial, at what point they're able to either hear or not hear, or see or not see, or detect or not detect the stimulus anymore. That's called the method of adjustment. The method of constant stimuli. Um, you've probably actually experienced this before with when you've done a hearing test. I don't know if you've ever done a hearing test. So you go into a little soundproof room, you put on some headphones, and they play different tones of different intensities. Um, the tones, and you're supposed to click a button if you hear the tone, press a button if you hear a tone, and not press it when you don't hear it. And basically, this is just presenting different intensities of sounds or whatever, right? Touches or sight in random order. And what you're doing is you're detecting the point at which the person can detect the stimulus 50% of the time. So that's the threshold. The threshold is defined there as the point at which they are 50%, they're able to guess it half the time. Okay, so for example, this is a picture of some data obtained by this method, right? So here we have light intensity going from uh, not so bright all the way to very bright, right? And then we said percentage of the stimuli that are detected. So across this test, when the light is at 150, whatever this is, right? I don't know what this measure is, but it's 150 something, right? Nobody sees it, right? There's basically 0% of the stimuli are detected. At 160%, uh, you can only detect it correctly looks like about 10% of the time. At 170, looks like you're hitting about 20% of the time. All the way till you get up to about 180. When you get to 180, this light, that's when you're able to see that light, that stimulus, about half the time. So half the times you'll see it, on average, half the times you'll see it, and half the times you won't see it. And that's the threshold that we're talking about here um, to determine this threshold. Of course, here, once you get to the 200 level of the intensity, of course, it's detected 100% of the time, meaning that that's as bright as it can get. The difference threshold, that's actually the DL that you see there. That's actually an abbreviation for a German word. DL is an abbreviation for Differenzelimen, which, as described in your textbook on page 14, at the start of page 14 there, Differenzelimen, which is a different threshold. And that's basically the smallest difference between two stimuli that a person can detect, right? So here's an example, right? Let's say, for example, you have a handful of sugar, right? So you're holding a handful of sugar. Let's say you're holding 50 grams of sugar, right? You have 50 grams of sugar, and you're holding it in your hand. And if I add one little tiny grain of sugar to that 50 grams, you're probably not going to detect. It's going to feel the same, right? Then if I add another and another and another, I'll keep adding grains of sugar. And at some point, you're going to be able to say, yeah, that is heavier, that it is changing, right? It has gotten heavier. That's the threshold. And then I would measure how much sugar I had added, and that would be the difference threshold for that amount. Um, so basically, and there's an interesting law, a relationship that's been identified here, and it's called Weber's law. And basically, that says as the stimulus increases, the bigger the stimulus, so does the difference threshold. And here's and the example would be this, right? With a handful of sugar, if you had like, let's say, 100 grams of sugar, it would take probably about 5 or 10 grams, right around there, before you would feel a difference, right? 5 or 10 grams. But then let's say it's 5 or 10 grams, right, for that little pile of sugar. Now, but let's say instead you were holding a 5 kilogram, 5,000 grams of sugar, right? And that's 5 kilograms is about the weight of like a backpack, right? Like your backpack. So let's say you're holding 5,000 kilograms of sugar instead of 100 grams of sugar, right? That's a huge difference, right? We went from 100 grams to 5,000 grams. Okay. Well, if you were to take that 5,000 grams, and you were to add that same 8 to 10 grams that I added to the first batch, do you think you'd feel it, the difference? No, you wouldn't. It would take more sugar. It would take with 5,000 grams, with 5 kilograms, you'd probably need about 100 grams of sugar or so before you'd start to feel a difference, or a couple hundred grams of sugar, really, before you started to feel a difference in the weight. Um, and that's because the magnitude of the stimulus went from 100 grams to 5,000 grams, right? So there's a proportional relationship between the size of the stimulus that you start out with and the amount that you have to add or subtract before you notice a difference. Okay. Another example. Let's say you have a candle, a single candle that's lit up and it's burning, right? If you were standing out in a bright parking lot, August noon and a noon day in August, right, in the middle of the parking lot, at UTSA somewhere, and somebody was standing in the parking lot, and about a quarter mile away you were standing looking at that candle, or looking toward them, you probably wouldn't be able to see that candle, the light from that candle, because it's bright and sunny outside, and you're a quarter mile away. That's the magnitude of the stimulus, which in this case is the sun, right, is overwhelming that candle, right? You would need a much bigger stimulus. Say, for example, a bright light from the police car, right? A bright light from a police car, you can see that. A high beam from a headlight, you'd be able to see that in the bright sunlight. It's a bigger stimulus. It's a much greater stimulus to deal with the greater sunlight. On the other hand, if you were standing in a pitch black, let's say you're outside and there's no stars, no moon, no lights anywhere, it's just pitch black, you'd be able to see that candle from a mile away. We can actually see single candles in clear, dark night from very far away. You'd be able to see that candle. The reason being that the magnitude of the stimulus, the background is very low, so it doesn't take that much extra light or extra stimulus for you to be able to perceive it. Okay. Um, Another method that we use for estimating magnitude, right? We want to be able to see how critters and people are able to um, guess how much of something is being given, right? So once we've determined the threshold, in other words, where the detection limits are, now we want to be able to see how far you can go. Whether you're able to detect changes in the magnitude, how powerful the stimulus is. So basically, what you do, say for example, you give a light, you shine a light, and you say, we're going to call this light a value of 10. Okay. Now what I want you to do is compare these other lights and tell me how bright they are relative to the light you just saw. So you'd say, okay, we're going to call that light 10, right? And then we're going to show you another light. You might say, oh, that's a 12, that's a 15, that's a 20, that's a 10, that's an 11, right? And this gives us a really good way of determining how well people are able to judge changes in magnitude relative to a standard measure. Okay. Um, you can actually calculate Weber fractions for different sensations, right? So remember, this is the percentage change that you need to be able to detect something. Okay. So let's look at the second one, lifted weight. Okay, lifted weight, 'cause that's the easiest one to understand, right? So let's say that this weight that I have here, right? This weight that I have here, let's say that this weight weighs 1,000 grams. So 1 kilogram. This weight weighs 1,000 grams. Now, if I were to add a single gram to this weight, I wouldn't be able to detect a difference, right? As you can see on this chart here, let me put my weight down. See this chart here, there's a 2%. It has to be a 2% change. In other words, the weight has to differ by 2%, either adding or subtracting before you're able to make a difference. So 2% of 1,000 grams is 20 grams, right? So if this is 1,000 grams and I add 1 gram to it, I won't be able to detect a change. But if I were to add 20 grams to it, then I would be able to say this does feel different. The weight did change on this. Okay.